Can you all hear me? Great, lovely. My name's Hillel. Thank you so much for coming to my talk. I realize I'm the only thing standing between you and food, so I'll try to keep this one a little brief. Let's say you're doing a code review, and you have, I don't know, 6 files you're going to give to them to look at. I'd like to start with one tip that will make your life so much better. Tell them which file to start with. If you do not do this, I guarantee they'll just look at the first file. Probably if they're using GitHub, the alphabetically first file, and focus all their attention on that and ignore the rest of the important stuff. And when I say I guarantee this, I don't just mean from personal experience, although that is true. I mean, this has actually been studied by scientists. In this paper, First Come, First Served, they looked at how people review code based on the positions of the files in the review set. And they find that for just 5 files, people write 40% fewer comments on the 5th file than the first. In other words, people look through the list top down and do not actually focus on what you think is important. You have to tell them what's important. And not only this, they also found that most people don't realize they're doing this. In a survey they did, 77 out of 106 people said that they give equal attention, or at least they can find flaws equally well in the first file as well as the last, when in their own studies they found that was not true. People were more likely to miss bugs found later in a code review than earlier. Before I was a software engineer, I was studying to be a physicist. Science and physics were my life, day in, day out. Then one day I realized that as much as I liked science, I liked money a whole lot more. And then I became a software engineer. But that fascination with science never really left me, especially when I started looking into how we make the decisions we do, the practices we use, and found that a lot of it isn't based on what objectively works, or even based on what we've experienced works, but based on what charismatic tech figures tell us. And often these charismatic tech figures disagree. Some might say that not using test-driven development is equivalent to medical malpractice. If you don't write your tests before your code, you are literally killing children. Others say the exact opposite, that test-driven development is like abstinence-only sex ed. If you practice it, you're going to make way too many children. And both these people are talking, yes, from the personal experience, but when we read this and we make our decisions based on this, we're essentially deciding what we do based on who is the best writer, who is the best speaker. And that always bothered me. I wanted to know if there was anything we knew about software engineering that has been looked at and has been verified to actually work. This field is called Empirical Software Engineering, the practice of studying how software engineers develop software. I hope I've already justified why this is an interesting topic to me, one very near and dear to my heart. So for the rest of the talk, I want to show what it actually looks like in practice, what it tells us or doesn't tell us about what we do, and how, if you're interested in this, you can learn more about what we've learned. Before I begin, though, I want to make one thing clear. I'm going to be throwing a lot of papers at you, a lot of papers. I'm not expecting you to write them all down. That would be cruel. Instead, I've made this website, hillelwayne.com/talks/esc/DDD, where you can see references to all of the talks I mentioned in this talk. Additionally, it has a copy of the slides, and if people ask me questions in the hallway track, I'll try to write them all down and upload my answers here too. So to start, a quick refresher on the scientific method. First, we observe the world and see its properties. We make a theory about how the world behaves based on this and see what it predicts about what we do. Then we come up with some way of testing this, and then we evaluate our test, either refining our ideas, abandoning them entirely, or sharing them with others. This has worked well in a lot of fields, although when it comes to humans, as we'll see, it does run into a lot of challenges. Usually, us layfolk, we think of this as the clinical trial, basically a form of A/B testing. You have something you want to study, so you take 2 groups, a control group and an experiment group. You make some change to the experiment group and see how that modifies what they do. Let's say you were trying to see what sleep deprivation did to your ability to code. First, you get a person and have them just do some kind of task. This is your control group. You've made no changes to them. Then you get a second person, and you have them do the same task, except you don't let them sleep the night before. This is your experiment group, or your treatment group. Then you compare the relative software qualities, and you see which one is better. From here, you can decide that sleep deprivation affects you, or doesn't affect you, or somehow makes your code better. I don't know. Make sense to everybody? Or are you starting to see some problems with this? For one, what's quality? I've read a lot of papers that try to measure software quality, and a lot of them don't do a good job of defining it. Or when they do, many of them use very unusual metrics that make no sense to the practitioner. For science to work well, there needs to be a constant dialogue between the scientists studying us and us being studied. One thing I would come up with as a practitioner is you give them both a task and you have an acceptance test suite. You compare how many tests each group passes. This isn't a perfect measure of quality, but it does find interesting patterns, I think makes sense to me at least. So let's say we do this for our test, and we find that, I don't know, the experiment group passes 5% fewer tests. In other words, missing a whole night of sleep makes you 5% worse. Now we've proven it, right? Again, there's issues with studying people. For one, there's lots of what we call confounding factors. Like, maybe the person in the control group has been doing this for 30 years, while the other person is barely out of a boot camp. Then, no matter how much sleep one person has or not, this person's probably going to do a lot. But wrong way, sorry, I'm using a new clicker. This person's probably going to be doing a lot better. And even if they have the same amount of experience, people do have different kinds of skills in software, right? Like, I work in a lot of mathematical software, distributed systems. If you ask me to prove a complicated Leibniz theorem, I'd be like, yeah, sure. If you ask me to do basic CSS, I'll pretend I don't speak English. Yeah. These, as mentioned, are called confounding factors, things that explain the results we get besides what we're actually trying to study. There are lots of ways that scientists try to control for these factors, remove them as possibilities. But the most basic, most important one is just adding more people. If you're studying 50 people instead of 2 people, differences in skill level, age, preferences, how hungry they are, how sick they are, all of it kind of gets smoothed out. Then again, 50 people usually isn't enough. When people do medical trials, they're usually doing it on hundreds or thousands of people. And this can cost millions of dollars. So when universities who do not have millions of dollars are trying to study software engineering, often it becomes very hard to use clinical trials to find subtle signals. It's only really good for the most part at finding really strong, really obvious signals, such as sleep deprivation. In this study, Need to Sleep, people actually did look at this. They had a group of 40 novice programmers, admittedly that is a confounding factor here, but 40 programmers, and had half of them stay up a whole night before doing a task. In their test suite, they found that the people who were sleep deprived passed half as many tests as the people who were fully rested. That's a difference of 50%. Not the kind of thing that is easily confoundable. So if takeaway number 1 from this talk is give a starting file in your code review, takeaway number 2 is get more naps. Of course, now that we have something that has such a big effect, this makes everything else hard. If, say, I'm studying pair programming and I find that the experiment group does 5% better, maybe the control group just missed an hour of sleep that night. It's going to be washed out by that effect. In short, clinical trials are very hard. So hard, in fact, that a lot of people think that software engineering as a whole is not studyable, that when faced with the hard problem of figuring out how to actually learn what we do, we should just give up. But this is a problem that all fields of science face, not just empirical software engineering. After all, if you're trying to see if smoking causes cancer, you can't just go into a lab and force a bunch of people to smoke, right? Instead, scientists often look for proxies to the clinical trial, things that aren't as high on the standards list, but still give us useful information. Many of these are natural experiments. This is where you're essentially looking for data in the wild. And this is, in fact, how we determine that smoking causes cancer. Scientists looked at the whole population, identified which subset are smokers, and then compared the rates that they died of lung cancer. They found that smokers died at a much higher rate than non-smokers. This isn't a smoking gun proving that smoking causes cancer, but it's a very strong correlation that encourages us to look further and make predictions. You can sort of think of the natural experiment as taking the scientific method, but instead of doing the test phase, you just observe a lot more. The question then becomes, what are you trying to observe? Where do you get the data? We've actually seen one of the common ways we get data, surveys, where you go out to people who've done stuff in the real world and ask them questions about what they did in their experiences. This is how we learned that most engineers doing code reviews think they're equally good at finding bugs in the first file as opposed to the last file of a code review, even when they're not. Surveys aren't necessarily that good at finding what works and what doesn't, but it's good at finding out what people think what works, or what they're trying to make work, or their opinions on things, and these are often very valuable things to know too. But most fields of science can do this. In software engineering, we have a slightly different thing, another resource that we can use that nobody else has, GitHub. On GitHub, there are approximately 300, 400 million public repositories of code, all with histories, most with pull requests, most with issues, most with bug fixes all listed. And this is an incredibly rich source of data that we can use to learn more about our field. One paper I really like is this one, Simple Testing Can Prevent Most Critical Failures. They trawled GitHub to find issues that led to entire clusters of distributed systems going down. Then they were able to look at the bug reports and the bug fixes that were done to figure out what exactly caused the bug. They found that in 92% of cases, it was due to incorrect handling of a non-fatal error explicitly signaled in software. And they further found that many of these error handlers were just empty, containing a single comment saying to do or fix me. From this, they were even able to create a regular expression that could find entirely new bugs, undiscovered bugs, latent bugs in distributed systems. And they were able to suggest a lot of fixes that did prevent these things going forward. So takeaways. Starting file and code review, take more naps, write your goddamn unit tests. GitHub is a really good resource, and we've done a lot of great things with it. But it's also very easy to go wrong. When you have that much data, it's a lot of hard work to make sure the data is saying what you want it to say. In one of the most notorious cases of this going wrong happened in 2018. In this paper, a large-scale study of programming languages and code quality in GitHub, they were trying to figure out what languages led to more defects and which languages were more bug-free. They claimed that they studied 17 languages, 728 projects, 1.5 million commits, 17 languages, 63 million lines of code. And from that concluded that certain languages were more error-prone than others. They said that, for example, C++ was the most error-prone, while Clojure and Haskell were some of the least error-prone. This was one of the most cited studies in ESE for a long time, until somebody tried to replicate it. And by that, I mean go over the same data and try to see if they got the same results. Replication is extremely important in science. And what they found was that it did not replicate. And the reason why was because the original group did not clean up their data. They found bugs by looking through commits for words like error, bug, fix, issue. Then, when the replicators looked through all the commits they listed as bug commits, they found that 40% of the commits were things like this: fix typos in docs, add bug reporting instructions, improve the infix operators. None of these actually matched bugs. They were false positives, spurious information that the original paper forgot to filter out. And this made all of the results suspect. I thought I had a link to learn more about this, but it's on the website. You can read a 6,000-word write-up I did of this entire saga, basically the paper, the counterpaper, the counter-counterpaper, et cetera. Anyway, that's one problem with natural experiments, messy data. Another problem is that you don't have access to the full picture. You can see on GitHub what code was written when, maybe even by who, but you can't see what process they used to write it, what they were thinking when they write it. That stuff is called qualitative data. Instead of quantitative being numbers, qualitative is the fuzzier stuff. we can do this in a lot of ways. We can interview programmers, and we can observe them from a distance, watch how they work in day-to-day, and shadow them, essentially. There's a lot of different ways we can do qualitative research, and while it's often sort of neglected by us layfolk, we don't really think of it as science. The more I've learned about this field, the more all of my favorite papers have all become qualitative papers. It just gives you so much richer information, even if it doesn't necessarily know which of that information has been verified totally. One such paper, and honestly, one of my favorite papers ever written on this subject, fixing faults in C and Java source code, abbreviated versus full-word identifier names. What they did was they took a code base and seeded it with bugs and gave it to groups of developers to fix those bugs, watching how they worked. But critically, half the engineers who got this were given full name identifiers like employee reservation ID. The other half were given abbreviated identifiers like EMPRID. They found that these people worked through the code file in totally different ways. The people with the full names tended to skim and jump around, using the full identifiers as anchor points and doing what they called opportunistic bug fixing, chasing intuitions and the ideas they had on the spot. The people with the abbreviations instead worked methodically through it, understanding the broader structure and semantics and control flow, only going down and lexically expanding an abbreviation after they were sure that it was relevant to what they were trying to do. So these are two totally different ways of looking at code and doing debugging. And people were unconsciously choosing which one they did based on the information they could parse from the identifiers. And I think this is also a valuable takeaway. Be mindful of how you're reading your code. Notice whether you're doing something opportunistic or methodical, and try to ask yourself if it's the right way to be approaching the code you're currently doing. This is the kind of stuff that only really shows up in qualitative research, which is why I love it so much. So a quick recap of what we've seen so far. 1, science is very hard. Lots of ways it can go wrong. 2, lots of ways we can do it. Clinical trials, natural experiments, qualitative experiments, interviews, observation. A whole lot of ways I haven't talked about yet. These are just the broad strokes, each with their own benefits and drawbacks. Now, this is how it all works in theory. In practice, things get hard. One way things get hard is just the natural mode of human existence. Not everything you read is going to be very good. You have to be careful to make sure papers are saying what you think they're saying, that they do their data analysis correctly, that they're drawing conclusions that are warranted, etc. The other problem is a little bit more frustrating. I work professionally in a field called formal methods. I train companies on how to specify abstract systems, create designs that can be directly tested for bugs. I found this is an incredibly effective way to build systems faster, more safely, more cheaply. And when I got into empirical software engineering, my first question is what I'm doing verified? What does the science say about my practice of formal methods? So here's what the science says. I still believe in it personally. I've had personal experiences showing how effective it can be. But I have to admit, I don't know on a broad scale how well it works. It's not been verified. I'm working on my own experience and my own faith. That's okay. We all do. But I have to be humble about what I'm saying. I cannot be too arrogant about my claims. I cannot be too boisterous, simply because I know there's no science backing me up. The reason why so few people have studied this is quite simple. For every person studying software engineering, there's about 10,000 software engineers actually doing software engineering. And if there's one thing that's amazing about our field, it is how quickly we come up with new ideas. Software engineering is one of the most communicative industries on the planet in terms of how many ideas we share and how open we are with our ideas. This means there's a lot of things to check, far more than anybody can do in a single lifetime, far more than teams of people can do in a single lifetime. So scientists have to pick and choose what they focus on, and right now, formal methods, my specialty, just hasn't been a priority. It might never be a priority, because by the time people get around to it, there could be 10,000 new ideas we have to look at. But there's still some stuff out there. And if you're willing to look, in most fields, you can find at least a few interesting papers. This, though, is a skill. Just like programming is a skill, and just like doing science is a skill, researching science is also a skill. And I thought I'd like to show you what that looks like. As my example, I'll pick something that I think is relevant to this conference. What does the science say so far about DDD? DDD is a relatively small field compared to things like tests or code review or modules, but there have been at least a few people looking at it, and I thought I could parse out some information. I do want to make a disclaimer here, though. I'm not a DDD practitioner. I read the book after I got invited to this conference. So I do not have enough personal experience to verify many of the claims I'm reading. I found a DDD expert, Chris Simon, thanks to him, who was patient enough to let me ask all the things I noticed and ask him whether they made sense or not. That way I was able to rule out some stuff that I thought was just a bit too obvious for people and try to focus on what's interesting. If I make any other mistakes about DDD, it's my fault, not his fault. So how do I learn about this? I'm going to be covering a lot of papers, by the way, so again, go to the website if you want to read the papers I talk about. And I'm not going to talk about all of them because there's just too many, but I'll focus on some things I find interesting. My first step is to go to the site called archive.org. Most science is done in paywalled journals. That means you have to have a subscription to the journal to read the article. But a lot of scientists despise this. It's enforced on them by the system. They hate this. They wish their research was open and free. And so what a lot of them do is they publish their first draft on the site called archive.org. arxiv.org, again, link will be in my website. Here you can read all the first drafts that people have, or at least most of them. Usually the final drafts are like a little bit more polished or like a bit fancier, but all the data remains the same. Also, it's way easier to search this than search the entire internet. What I'm looking for is called a survey paper, a paper that goes through and tries to aggregate all the research that's already been done about a field. I was able to find one such survey paper in DDD. Domain-Driven Design and Software Development, a systematic literature review. This covered 36 papers and books on DDD to try to find common patterns. And there is some interesting stuff in here. Like they say that almost all the papers talked about ubiquitous language and bounded contexts, but very few of them talked about anti-corruption layers, suggesting it's not as common in DDD circles to apply this idea versus other broader ideas. But far more importantly from this paper, I got references. In science, if you write a paper and you're talking about something, you have to include a reference. You have to include some way for somebody to check your claim and look to see if you're actually making the claim you claimed you're claiming. So if there's 36 papers they used to make the survey paper, that means there's at least 36 references, all in this reference set. But notably, these papers are also going to reference other papers. And in this way, by jumping from paper to paper, I'm able to build a web of interesting papers. In some cases, I'm even lucky enough to go the opposite way. Some tools let you take a paper and find what cites it, and that way I can find entirely new papers not in the network, and then find their references. After this, I had maybe about 30, 40, 50 papers that I thought were worth reading, and then you grind. Sit down and you read everything. After about 2 weeks, I went crazy, my friends stopped talking to me, suddenly it started burning my skin, but I had a better sense of what the actual field looked like. And I'd like to quickly cover some of the papers that, as an outsider to me, looked interesting and might have value to you. I'll cover 3 groups of them. Paper number 1 was this one called Design, Monitoring, and Testing of Microservices. It was a qualitative natural experiment paper. It involved both interviews and surveys. They were trying to figure out what techniques people used and how they used them when trying to migrate monoliths to microservices. What they found was that a surprisingly large number, approximately 70%, used domain-driven design in some form. 30% used it by its own, 43% used it in combination with business capability, which, as I understand it, is mostly like building microservices according to the org chart. The one note about this there's a couple of interesting caveats that they had. One of the caveats that I thought was unusual was that many of the people doing this did not have formal training in microservices. It's not clear whether they meant that these people did not know DDD when they tried to apply it, or if they knew DDD but didn't get any training in how to apply it to microservices. Just a thing of note. They also interviewed people to find out reasons they did not use DDD. 2 of the reasons people claimed, things they were worried about, One was what happens when the bounded domains contrast with the business organization chart. The conflict between DDD and business capability was a large concern. Another large concern was that too many people were afraid that it would cause performance regressions. They thought that the business domain was different enough from the software domain that building around the business domain would hurt the software domain. Now, again, I don't know if this is true or not. I'm going to assume it's not true. But this is what people worry about, what they fear. So if you're going to pitch DDD to a company to build microservices, these are probably going to be two of the objections you'll have. They should be things you should be prepared for. I do also want to note at least one confounding factor in the study. Almost over half of the people in the study came from one geographic region. So it could be a very regional thing. They said that the people in the outside this region did have similar distributions of whether they used DDD or not and how they approached it, but I'd want to see a larger sample size for this kind of thing. Paper number 2, practitioner views on the interrelation of microservice APIs and domain-driven design. This is called a grounded theory paper. What they did is they looked at approximately 40 case studies of trying to use DDD to build microservices. And they tried to figure out what the common themes and patterns were, what people were thinking, issues that everybody faced in common, things like that. Now, this paper is really dense. It has a lot of really detailed stuff, and I really recommend reading it. It's a very good paper. I'm just going to focus on one small thing here really quickly, is this. The differences in how people tried to map the API to the domain. They noted that many people initially tried to just make the whole domain model a one-to-one relationship with the API, and everybody claimed this had a lot of problems. They found that people tended to settle on one of two patterns. Either you take each bounded context in your domain and you make that a separate API set, or you take some bounded contexts and make those internal to your system, and then some bounded contexts are external. They have external APIs. Everything else does not have an API. They mentioned some of the trade-offs people claimed in both these choices. Again, the paper itself goes into much more detail about this. The third thing I'm noticing I want to call out are these two papers that are called action research studies, refactoring and domain-driven design with industrial context, and tackling consistency-related design challenges. An action research study is one where the scientists study an organization, and then they come up with a plan to try something, either new concurrency patterns or applying DDD to a refactoring. And then they work with the team to make this implementation, and then they interview the team afterwards to sort of see what they liked and didn't like, the problems they had or didn't have. Basically consulting, but science-y. And again, both these papers are pretty long and dense. They go into a lot of details, so I'm bringing them up because I really do recommend reading them. But I don't think there's anything I can pull out right now that would like any sort of specific claims I want to share. I just want to point out these papers and this kind of approach to doing science. And again, all of these papers are at this link. Even if you believe me in everything I say, I do recommend reading them. And especially if you don't believe me, I do recommend reading them. Because one of the most important things about science, and one of the reasons it's so precious to me, is that it's public. If somebody makes a claim, they will try to present the data they have for the claim. You can look at the data they have. You can look at how they got from the data to their end result. You can look at the math they used. You can look at their confounding factors and their threats to validity, what could have gone wrong. If you find issues, that's important. That's part of the process. We look at these things, these claims, and we evaluate them. Even claims that we like, we evaluate seriously and try to make sure they're rigorously done. And if they're wrong, well, that's good to find out too. Science is a slow, halting, difficult process, but it's one of the best we have to learn things about the world. So, brief conclusion. I realize I'm way under time here, but that just means you get lunch earlier. Conclusions. 1, science is hard. 2, doing science is hard. We're not very good at it. 3, be skeptical of the claims you hear, both backed up by science and not backed up by science. Look at the things, decide for yourself. I'd like to wrap this up by just mentioning a few of the good resources for finding these papers. If you want to research more about what we've learned, where you can go. First one is, I already mentioned the first one, that's archive.org. The second one is the ACM Digital Library. How many of you have got an ACM membership? OK, not many. The only reason to get an ACM membership is the digital library. Almost every single computer science paper published, not all of them, but almost every single one, is free and searchable on the digital library if you have a subscription. You can also do things like sort them by tags, search for related papers, collect them into like binders organizations. Just an absolutely fantastic tool if you're trying to do any academic research into computer science. But it also costs £100, which I know not everybody really wants to pay. Sorry, €100. It costs $100. But I'm going to assume they charge €100 because trying to like adjust for currency differences just seems like a bad idea if you're an international company. If you don't want to pay the €100, you can use the site I do not recommend because it is illegal, called Sci-Hub. Sci-Hub is very illegal and lets you skip paywalls. You put in the link to any paper, and it will give you just the paper. No need to pay the $40, the subscription, buy the journal, because looking at these papers, if you're not part of an academic institution, can cost a lot of money. But again, very illegal. I'm even going to leave this up for a bit just so you know exactly what to avoid. If you stumble into this, know exactly to leave it. If you want, you can just like cut out this entire part, just replace it with static. Your choice. And finally, I'd recommend a few introductory books I really like. The first one is called Teaching Tech Together by Greg Wilson, and it's specifically designed to help people who want to teach computer science to beginners do that better. But it is chock full of great references to really good stuff on how we learn how to program, what works best in educating people, and how the mind approaches programming as a topic. Also, it's free online at teachtogether.tech. I'll have a link again in my description. I do want to, as a quick disclaimer, say that Greg Wilson is a friend of mine, so I'm just shilling him. Second book, The Programmer's Brain by Felina Hermans. This is a book about the intersection of expertise, psychology, and programming, how our minds work and how that relates to the programming work we do. Again, very good book, very well written, a lot of citations and sources that you can follow up on. She also is a local. She teaches at Vrea University. Also, disclaimer, Felina Hermans is also a friend of mine. Last book I'll recommend is The Leprechauns of Software Engineering. This is a book about a person who's actually really skeptical of ESC as a topic. But what he does is he finds claims that people say are proven to be true, like bugs are more expensive in production than in design, and then tries to find the root of where that comes from, chasing down all the papers and the references to find where these things originally formed. So it's a great look at how to do the process of researching software, how to do the process of researching ESE. Disclaimer, Lauren Bosavi is a friend of mine. OK. And even if you decide none of this is interesting to you, even if you decide that science is stupid and you don't want to talk about it again, think about it again, I do want to list the takeaways that I have, just the short lessons that we have found that do make a big role in how well you can write your code. Step 1, if you're giving a code review to somebody, tell them the file to start with. Otherwise, they will start at the first file, which may not be the file you want them to look at. 2, take more naps. Coding while sleep-deprived makes you worse. 3, write your unit tests. They do catch really critical errors that can cause millions of dollars in damage. 4, be mindful of how you read code. The ways that you approach code are done unconsciously sometimes, and if you know what you're doing, you can change how you're looking at it. And 5, hire me to teach a formal methods workshop. If anybody has any questions, I'm happy to hear them. Thank you for coming to my talk, and once again, thanks to Chris Simon for looking at my questions and fact-checking them. Thank you.
Thank you so much. And I was wondering when you mentioned the first book when you were going to mention Felina, so I'm happy you did.
Yep.
We do have a cube for questions, so if any of you have questions, raise your hand. We will throw the microphone cube at you, and then you can ask Hillel your questions. I think everybody wants to get lunch. Mm-hmm. But that's totally fine.
Yeah, I'll also be around like for the rest of the conference, so if you want to have a question, just corner me. Ask it to my face. Don't even introduce yourself. Just shout as loud as you can. I'm fine.
Which means you have almost 2 hours for lunch.
Oh, there's somebody over there who has a question.
Oh, question?
Yeah.
Can you throw the cube that far?
No. I will need help.
You can do it in 2 relays or whatever. OK. Just speak into the black part of the cube.
Yes. Hello world. Can you hear me? Okay, nice. So you were showing these abbreviations versus the fully written terminology.
Yes?
And I wasn't quite sure on which exact conclusion did you draw from that. So you were saying that the abbreviation led to the developers taking more detail into account, going through everything step by step and getting a deeper insight. What conclusion do you draw from that exactly?
So the conclusion I draw from this, one of the things so there are a couple of things I did not mention about this. One is that they said that both groups converged on the right problem equally quickly. So it doesn't necessarily mean that one's better than the other. What I notice is that it's a very unconscious process. They are looking at the code, and based on the identifiers they see, they change how they read the code. And just knowing that what the code looks like changes how you look at it seems really valuable to me. It lets us basically notice, hey, I'm reading the code in a certain way. Based on unconscious cues inside the code, is this the way I actually want to be looking at it? If I'm debugging a concurrency bug, I want to be very, very methodical, right? But if I'm looking at other code bases, I want to be jumping around. I don't want to decide what I do just based on the identifiers I see. Incidentally, they did also notice one really interesting thing they noticed about the difference is that people with abbreviated identifiers were way more frustrated trying to do text searching because they didn't know what the abbreviations were and they didn't know exactly how it was abbreviated. It was much easier for the people with the full identifiers to find the things they're looking for via search. And that's one of those really subtle differences that I don't think can be found without doing this kind of qualitative research. Incidentally, the paper is also tied to another quantitative paper where they measured how fast these kinds of debuggings happened. Really good paper. I love it. It's one of my favorites.
Yeah, thanks a lot for elaborating. And thanks for the great talk. I really appreciated the humor beside the facts themselves.
I'm glad you enjoyed.
Yeah. Where do frauders now?
At the next person raising their hands.
I think everybody's afraid of holding people back more because now the next person raises their hand, they're now holding everybody back from lunch.
Yeah.
So
also, they're maybe scared that they'll get the cube thrown at them.
Yeah.
Right. Yeah.
That seems kind of fun.
It does. All right, you're all excused. So enjoy your lunch.